Okay, gang, looks like I'm going to try this again. This is my third shot at this tonight. So, this is the musical instrument notes. It should be Wednesday. This is our second day of notes for our waves and sound test. We started our first set on Monday, and we dealt with Doppler effect and everything, and hopefully yesterday you guys worked on those problems. So today we're going to talk a little bit about musical instruments. I may break this into smaller pieces and see if I can get it done better than it being one giant piece because it hasn't been liking me very much trying to do one piece altogether. So with that, you should be adding these to your notes and you should have your simple harmonic motion and waves vocabulary out because we've been added pieces to that. Now, sound comes from a vibrating object. If an object vibrates with a frequency and intensity within the audible range, which remember is 20 hertz to 20,000 hertz, then it produces sound we can hear. The musical instruments that we will be talking about will be string instruments like guitars, violins, and pianos, and I write those down as examples of string instruments, as well as wind instruments, which would be open pipes like flutes and organs, and then closed pipes, which would be things like clarinets, oboes, and saxophones. You should write those instruments down in your notes so that you can go back and look at problems and say, is a saxophone open or closed? Those kind of things. And then we have percussion instruments. We have drums, bells, and cymbals. We don't work with them quite as often as we do the strings and the wind instruments, but we will but they are instruments. So make sure you get the string instrument examples and the wind instruments of open and closed pipes down in your notes. Now, as strings vibrate, it sets surrounding air molecules into vibrational motion. This is called a forced vibration. So the frequency that the air molecules vibrate is equal to the frequency of the guitar string. So this should be something that's in your notes. And a forced vibration is the vibration of an object caused by another vibrating object. So make sure that that's in your vocabulary. I'm sorry, I said notes a minute ago. But make sure this is in your vocabulary. We talked about standing waves on Monday, and we talked about how we have nodes and antinodes, and this is a lot like the Wiggler Lab, which we did last Thursday. There can be more than one frequency for standing waves in a single string. Some of y'all saw that when you did the Wiggler Lab, but we talked about how this is one antinode, and so this is our fundamental frequency or our first harmonic. There was two antinodes here, so this was our second harmonic. Three antinodes, so third harmonic. Now the nodes would be where this complete destructive interference occurs. So you can say that these fixed positions are nodes. You could also say that this middle part is just the node. That depends on what publisher you're talking about. Most of the time I say that this is a single node. This has two, this has one, two, three, three. And so you can look at it that way, but you can also look at it that these ends are nodes as well. Okay. Sounds by vibrating strings are not very loud, so a lot of stringed instruments use resonators. This is a vocabulary word that you need to have. A resonator amplifies sound by creating a greater area in contact with the air. A resonator amplifies sound by creating a greater area of contact with the air. On a guitar or violin, the length of the strings are the same, but their mass per length is different. That changes the velocity, so the frequency also changes. Remember, frequency and velocity are related by wavelength because V equals F lambda. Okay. So again, standing waves there are created by interference, and they result in nodes and antinodes. These would be our nodes, or these null points, and these would be our antinodes, where the maximum amplitude occurs. Okay. In standing waves, the ends are fixed, so they will be the nodes. The wavelengths have a simple relationship to the length of the string. The lowest, or the fundamental frequency, only has one antinode, so that's really only half of a wavelength. So we could say that L equals 1/2 of a wavelength, or we could say that wavelength equals 2L. If we say that wavelength equals 2L, then when we talk about harmonics and frequencies, what we're going to do is we're going to say that the first harmonic is the fundamental frequency. The two antinodes is going to be our second harmonic, and so on and so forth. So the antinodes will match the harmonic value. Always. This is always true. The number of antinodes will match the harmonic value. All right. Now the equation for strings, if we use the basic equation of V equals F times lambda and rearrange it, then the frequency in strings would be the velocity divided by the wavelength. Well, we said the wavelength in strings is 2L, so I can replace that right here. This N value is the number of antinodes, so it's our harmonic value. So F is frequency in hertz, N is the number of antinodes, L is the length of the string in meters, and V is the velocity in meters and meter or in the medium. So in the string itself, in meters per second. Okay, an example, what's the fundamental frequency of a viola string that is 35 centimeters long when the speed of waves in this string is 346 meters per second? I have to convert the length from centimeters to meters. I know the velocity. I also know that's the fundamental frequency, so my N value is 1. So I'm going to use F equals NV over 2L. So I'd have 1 times 346 meters per second divided by 2 divided by 0.35 meters. You should be able to use your calculator to figure this out, and it's 494.29 hertz. If I wanted to find the third harmonic of this string, then I just take this fundamental frequency and multiply it by 3. You could also rearrange or do the formula again and instead put 3 in for N. So both ways would work, and you'd end up coming up with 1,482.86. All right. I'm going to stop there for now. I'll start another recording with wind instruments.